saw some sort of glassy-eyed, puzzled expressions at the end of the last time. I must apologize. I realized I wasn't expounding probability very well. Some people say you can't, but my problem was that I didn't think I was going to finish that other topic, so I hadn't, so to speak, prepared for class, and I had to start off without having looked at notes, and so as a result it was not the most brilliant integrated presentation. And from some things that people asked me after class and in the hall later, I realized that I probably did your cognitions more harm than good, so I'm going to do the last 10 minutes over again today. And those of you who understood everything with blinding clarity, it won't do you any harm to hear it again. Let's see if I can do it today. The kind of probability that we are familiar with as psychologists and the kind that we normally talk about in ordinary life is what among the logicians is called probability 2. And for us it would be probability 1, the familiar, usual one we learn in a statistics course. And it is a percentage or proportion or relative frequency with which some individuals or events have some property. That's what it's about. If I have a series of happenings like flips of a penny, I can ask, what percentage of time do I get heads? If I take a group of people who are insured by Prudential, and they're age so-and-so, and male, and Caucasian, and they live in the continental United States, blah, 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 and I ask what proportion of them will be dead in 5 years, that's a proportion or a percentage or a relative frequency of a class of objects or individuals. So whether we have a sequence as flips of a coin or throws of a die, or a collection given all at one time, in either case we can ask what proportion of the members of that batch, whether it's strung out in time or whether it's in a box at one time, what percentage or proportion of that batch has some attribute, like coming up heads, or being schizophrenic, or dying in 5 years, or having an automobile accident, and so on. So the subject matter of probability 2 statements is events or objects and the proportion of those objects or events that have some property. And so it's a decimal ranging from 0 to 1. It is a closed interval mathematically, because if we say something is certain, then its probability is 1. The converse, I remind you, doesn't hold. The fact that its probability is 1 does not mean that it's certain, because I can have a relative frequency. Well, as von Mises says, I can have a thing like this: heads, tails, heads, heads, tails, heads, 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 tails, like that. And that wouldn't be a good collective for von Mises because it's not random. But what is the limit to the relative frequency of heads? It's 1 mathematically. But of course we don't say that heads are certain because there are tails in the series. So the certainty of an event or an attribute in a class or sequence proves that it has p equal 1. But the fact that p equals 1 does not prove mathematically that it's certain. So since this kind of probability quantifies the proportion or frequency of attributes or events, attributes or properties of some physical objects or events, people are physical objects, it's in the object language. Its subject matter is the happenings or the individuals that this particular discipline, whether it's sociology or economics or engineering or chemistry or genetics, deals with. It's object linguistic. Now, I emphasize the von Mises definition of probability, which is the one that speaks of the limit of the relative frequency. relative, because in the numerator is the proportion of cases having the property, and the denominator is all the cases. But that's not the only kind of frequency notion. Some people prefer not to get hung up on this concept of probability as a limit of a relative frequency of an empirical series because of these mathematical paradoxes I mentioned last time. And they're not happy about the way you have to construe the law of large numbers if you're that kind of frequency person. The other name here is Reichenbach. And going back in the 19th century, John Venn wrote a famous book on that called The Logic of Chance. He was, in a way, the first relative frequency theorist, The Logic of Chance. That's the Venn of Venn diagrams. And another fellow named Ellis, about the time of the American Civil War, wrote about this. So those are the big names of that type. Well, people who don't want to define probability in that sort of quasi-empirical way, who want to be mathematically more elegant and who don't want to get into certain of the paradoxes that von Mises got into, use a formal definition, or what's sometimes called simply an axiomatic one. And that is connected with the name of the great Russian mathematician Kolmogorov, who I believe is still among the living, who wrote a famous book, which I have not read, in 1933, Englished in about 1950 or 60. And now, in that approach, one proceeds in a way that mathematicians like better, and that is one introduces a primitive concept, pi, calls this probability is pi, and one writes some axioms about its value. I think that Kolmogorov only had 3. Anybody correct me on that if you know about? I mean, it's amazing what you can get out of what little bit of assumptions. This number p or pi has to lie in the interval 0, 1. Well, closed interval 0, 1. And there is conceived to be a set of some kind that's associated with different p's. There's an attribute associated with pi, p1, and there's an attribute that we associate with p2. He talks about this in terms of sample spaces, and we get down to out here to a, k, pk, and then you make the further axiom that the sum of all of the p's from I equals 1 to k must equal 1. Haven't said a word about frequencies here. Just said there's some number p. It lies in the closed interval 0, 1. And the p's are associated with attributes or something. We keep it real abstract. And there's a finite list of those, and the sum of the p's that goes with them is equal to 1. And then if we have a's that are disjoint, ai, aj, the sum of all the p's, of all the a's that you can write, not all the a's you can write down, but any set of a's, is the probability of getting either a1 or a2 or a3. And that is, you learned in high school algebra or college as the law of addition for the probabilities of mutually exclusive events. I didn't say exhaustive here. This is the exhaustive part. Just that the events are incompatible, so that if you've got AI, you don't have AJ, and if you know the P's that go with all those I's and J's, then what's the P that you attach to a set defined as this disjunction of the sets that you've mentioned? It's the sum of the P's that go with all of the A's. Still nothing about relative frequencies. So that makes, out of that, believe it or not, you can generate the whole darn calculus of probability. I've always found it hard to swallow, but I'm not a mathematician. you get the multiplication thing out of there, for instance. And what you do with that kind of a system is you have to work out some kind of coordinating linkages of these p's that you derive out of that calculus with relative frequencies. That's the part that I've never quite understood, probably because I haven't read Kolmogorov's book, but that's the way they do it. So that they got a formal axiom system, like a scientific theory, and then you connect certain things that appear in there with empirical proportions. And apparently you can get the law of large numbers out of that in a way that doesn't involve the oddity that you have with the law of large numbers in the case of a von Mises thing. A third way of doing that in recent years, connected with the name of Sir Karl Popper, is to take this formal axiom system, although Popper believes that Kolmogorov deceived himself that you can get all you need to do probability calculus with only those 3 postulates. So Popper has some more of them. He introduces an interpretive term, propensity, which is like a disposition or a tendency, and then he combines this formal axiomatic kind of business with the concept of a propensity to make the tie-up with a relative frequency. So he derives that, so to speak, whereas the Kolmogorov type people, that's a basic, some kind of a basic postulate that enables them to link some of the derived p's they get in the calculus with frequencies of events. So these are all forms of interpretation of probability 2. Now Fisher is a frequentist in the sense that he focuses entirely on probability 2, but if I said, and I'm not sure whether I said this, but if I did erase it, I should not have identified Fisher with the von Mises interpretation of the thing. You can be a frequentist and not be stuck with von Mises and Reichenbach's definition, mind you, of probability as a relative frequency. The people who do not introduce that as a definition show it as a theorem. That's the point. Instead of saying an empirical sequence like throwing coins or dice or whatever, in fact converges to a certain limit, as far as we know it does, and that's my definition of pi for that sequence. They don't do it that way. Instead, they introduce pi axiomatically or formally, or if you like, you could say by an implicit or contextual definition, like in pure geometry. And then they prove something about how this will be related to a relative frequency. As I say, I'm not clear exactly how they do that, but that's the allegation that you can, via the Bernoulli theorem, you can show that p will tend to go to pi as n increases indefinitely. Well, all of that is in the object language, I repeat. Its subject matter is happenings, people, schizophrenics, politicians, fruit flies, genes, molecules. Now, what most psychology students have trouble with in this class when I talk about the other kind is due to the fact that they learned about this in a statistics course in which it was presented as if it were the only kind of probability that there is, not even controversially. I'll bet that almost every one of you had that experience. You were told about probability in the stat book, and the lecturer talked about it, and you talked about throwing dice and linkage of genes and stuff, and probability of a uranium atom disintegrating. And nobody ever said, now, that's one of the meanings of probability, but there's another meaning that's equally important in ordinary life and in science, not just ordinary life, and in the law courts that doesn't look like this at all. I didn't say it couldn't be identified. I said it doesn't look like this at all. Now, that other kind of probability also appears in common language. One says, I think it, I think it probable that those, what was it, 40,000 Polish officers that were dug up at Katyn were actually killed by Stalin and not by the Nazis. That's the opinion of most historians today. Stalin did it, and not Hitler. And between us two quick change artists, I'll leave it up to you. But anyway, I mean, when you kill 6 million people and somebody else kills 12 million, picking them differently, why, I don't know how you make a moral judgment. Be that as it may, when I say it's probable that that was done by Stalin and not by Hitler, where's the relative frequency? It's hard to imagine what the heck I would be talking about if I said what proportion. It's not as if we said 78% of those officers were killed by Stalin and the other 22 by Hitler. That's not what you mean, obviously. Or Caspar Hauser, Reichenbach's favorite example is Caspar Hauser was the son of a prince. He figures that makes it hard for his theory. Caspar Hauser was some guy that they dug up, and they found sort of like the wild boy of, I don't know, this goes back to, I don't know, 1800 or something, maybe earlier, and he had a peculiar property. He could see the stars in the daytime, and he was, what he was clinically, nobody knows. So, of course, somebody like that, tales spring up that he was the son of a prince and that somebody spirited him away to liquidate the dynasty or whatever. All right, Reichenbach says, it seems very improbable on the available evidence that Caspar Hauser was the son of a prince. Where's your relative frequency? I mean, you're not going to compute. You only have one Caspar Hauser to start with. There are not 18 of them. And it doesn't seem to make any sense to ask that. Or if I say, when poor old Wegener invented the theory of continental drift, having been struck with the way the continents look, you know, Africa and South America and all, everybody poo-pooed him, and poor fellow died, and although he wasn't resurrected, his theory was, and is now the generally accepted theory among the geologists and geographers, namely the tectonic plates doctrine is a souped-up form of Wegener's theory of continental drift, and supported by all sorts of interesting chemical and magnetic things at the bottom of the sea and all that stuff. So we say, well, on the available evidence today, it seems very probable that that's the origin of the continents, and that we're floating around on these plates. It makes you a little nervous when you dwell on it. I always wonder whether geology is a reassuring science. But again, if I said, what's the relative frequency? We wouldn't be thinking in terms of what percentage of all the planets, if there are planets, for example, on other suns, which is still disputed, but if there are, and we say there are 10 to the 15th planets in the whole big shebang, what proportion of them have tectonic plates? That's not what we have in mind when we say this. If there weren't any other planets at all, even in our own solar system, we would attach a meaning to the statement that this hypothesis seems very probable on the facts we have, right? Now, the facts that we have to support a scientific theory may themselves be of a frequency or statistical character. That's a different question. Sometimes the facts that we adduce to support our hypothesis are themselves of a statistical nature. But it doesn't follow from that that the connection between those facts and the hypothesis can be stated as a statistical frequency. Right? So, if we were to say, well, what's the probability that schizophrenia has something genetic about it, that maybe only a few people with the talent ever develop it, but you can't get it without having the talent, we would say the evidence on that is, except for frenzied environmentalists, very persuasive today. But can you attach a p-value to that? You can attach a p-value to bits and pieces of the data there. If I say, if I have a monozygotic twin who's got schizophrenia, my lifetime risk is, what is it now? It keeps moving around, but say 55%. Better than half, anyway. And if I have a sibling or a DZ twin that has schizophrenia, my lifetime risk is maybe 8 or 9%. And if I have a parent, then my risk is 12, 13, 14%. Going in the other direction, if I have a schizophrenic child, my risk is quite a bit down. It's only half as big. It's 5 or 6% from the latest table in Gottesman and Shields, Volume 2. Those are statistics. Those are relative frequencies. So they're probability 2. But now when I say on the basis of those statistics I have concluded that, say, the dominant gene theory is false, that's not strictly a statistical thing. And similarly, if I say on the basis of all of the evidence that's come out now on soft neurology and the psychophysiology of schizophrenics and their first-degree relatives, like the P50 anomaly with the evoked potential business and the eye tracking defect, and some other soft neurology like dysdiadochokinesia, oddities about postural sway. Some of that stuff goes back to Kreplin, I believe. And we say it looks as if schizophrenia is, while it's a mental disorder, arises on the basis of some kind of neurological or neurophysiological anomaly of genetic origin, but that there must be other events, environmental events, maybe sunspots or bad diet or battle-axe schizophrenic mother that help to develop schizophrenia. Since on any of the models, having the schizophrenic genotype does not give you a high probability of developing the illness. On the dominant gene theory, it has to be as low as 10%. Well, the point is there, what one has to understand is that the facts that are reduced to say it's genetic and that it's polygenic or that it's genetic and it's a dominant gene of low penetrance and any of those inferences, the facts that are adduced are of a probability 2 nature. They are proportions or frequencies. We can compute a numerical statistic and set up confidence belts and so on, but the relationship between those facts and the theory, the probability of the theory given the facts, that is not a number that we know how to compute by some algorithm that we find among the theorems of the probability calculus. We don't know how to do that. So that I can say, well, your odds if you have an MZ twin or so-and-so, and your odds if you have a DZ twin of the same sex or so-and-so, and I can go on spinning all those statistics out, and then I say, and since all of those things are known to be true with high probability, now I conclude with high probability that it's a genetic disorder of low clinical penetrance, blah, 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 like that. And then you say, well, what's the p-value on that statement? What's the p-value connecting T to F? Is it 78 or 91? And I say, well, I don't know how to compute that. I mean, I just point to these. Don't you find this convincing? And unless you're an environmentalist fanatic, you will say yes. And then I will say, well, what's the number on your degree of conviction? And you will say, well, I don't know. I just think it's very likely. How likely? Well, the Bayesian subjectivists, like Savage, DeFinetti, and some of our local statisticians, they say that if you do it right, you can always squeeze a number out of people in that type of situation. That means you can get people to say something about what they would bet. It does not, of course, tend to prove that they do it by an algorithm. And in fact, nobody claims to. It is true that you could get a number out of people. I used to have Professor Bowen from biometry give 3 or 4 lectures in this class until he got too busy. And he's a Bayesian, and he's a subjectivist Bayesian, which I strongly disapprove of. So it shows that I'm fair-minded because I had him in here to propagandize the youth. And he would ask people, what do you think is the probability that there's a planet that goes around Antares or whatever, and that it's inhabited? Or what do you, let's take a real distant galaxy that's 100 million light years away. What do you think the probability that there's life there? And the typical reaction of the students is wide and haven't even taken a freshman course in astronomy. I haven't the faintest idea. Well, you must have some notion. Oh, I haven't the faintest idea. Well, you must have at least a subject. No, I haven't the faintest idea. So then what he would start doing is proposing them bets of different sizes on other things. Like, what do you think is the probability that Nixon would flunk a lie detector test about Watergate? What odds would you give on that as against that there's life in this distant galaxy? And you push the person, and it turns out when you do that, I'm not very skillful at it, not being a subjectivist Bayesian, but he was very skillful at it, like a psychotherapist, Bowen was, and he could get the most careful, anal, skeptical student. He would phrase it so that this person would end up saying, no, that I wouldn't take 8-2 odds. I'd rather bet on this, you see. Gotcha, you see, he'd say. That shows that your subjective probability is less than so-and-so. So that's the way the Bayesians play it. And I don't dispute that people can be led or seduced or have their arm twisted to state betting odds. In fact, I'll come back to that because it's a very important, deep point. But that does not tend to show, and I don't know of any Bayesian that claims that it does show, that the way those odds are assigned by people is with an algorithm of the sort we use when we do the formal probability calculus on probability 2. This other kind of probability, which Carnap calls probability 1, and is usually called by that name among the logicians, including those who think that they can reduce one to the other. That is just as a matter of, you don't like to settle a debated question by semantic fiat, so that when somebody like Carnap makes a conceptual distinction, you say, okay, well, call probability 1 probability 2 for starters, then we'll have the debate as to whether they can be somehow identified. So this is not about the physical properties, but about relationships between propositions, or if you like, between beliefs. Most of the logicians would rather not say between beliefs because that makes it too psychological. Most logicians would rather say, since I think people could make mistakes in assessing probability 1, even if there isn't any algorithm, that means I want to distinguish between subjective relations between beliefs and what people, quote, should believe if they were totally rational. See? So that we don't know how to attach the probability to the statement that the Earth is flat, but I'll bet everybody here thinks that a flat earther is a nut. I certainly do. And most people thought they'd throw in a sponge when they had the moon shot, but if you know how people of that kind, how their head works, didn't faze most of them. They could explain, I forget how they did it, but it's a well-known phenomenon that if you are determined to stick to a certain hypothesis, it's always possible to do it come what may. Always possible to do it. The classic example in John Dewey's book, Inquiry, is the paranoid schiz who says he's dead, and the intern sticks a needle in him and makes the blood flow, and he says, see, you're not dead, and, well, by God, doctor, that proves dead people can bleed. See, you can't. That's the way it goes. So if you're a flat earther, there's no amount of evidence that will persuade you that the Earth is round, because you can always screw around one way or the other. A classic treatment of that, by the way, which you don't have to be sympathetic to Cardinal Newman to read with profit, is his book called The Grammar of Assent. After he finally threw in the sponge on Anglicanism and joined the Pope's Church, he continued to be worried about epistemology, and he wrote an excellent book called The Grammar of Assent. And his main example there is, suppose I ask, is Britain an island? Is it really surrounded by water? And you start bringing me the evidence to show that it is. And it gets very sticky. I mean, if somebody wants to drag his feet at every point, you know, and say, prove that, or does that mean this, or how'd you get from here to there, it is damn hard to prove that Britain is an island. It is very difficult if the listener is totally closed-minded on the subject. So we do make judgments sometimes about ourselves, in retrospect, more commonly about others, that they are not rational in the assessment of probability 1. And we say that a person who today doesn't admit that germs cause disease is being irrational, although Mary Baker Eddy could probably ad hoc that without too much trouble. And a person who thinks the Earth is flat is being irrational, is not assigning the right P to the relationship between the theory and the facts. I'm going to give you 2 examples of that, which I hope will convince everybody without further dispute that there is such a thing as probability 1, which is not, by any methods we have today, computable in turning it into a number by means of an algorithm. And the first is, did Bruno Hauptmann kidnap the Lindbergh baby? A famous case from my youth. There's a summary of the evidence showing that he did. Now, in recent years, his widow, he was executed for it in 1936. His widow has brought various lawsuits, and there's some debate about whether the prosecuting attorney was 100% honest in that matter. I do not want to address that question. If one presupposes the facts as described in that list, question, is it reasonable to think that Hauptmann didn't have anything to do with it? I mean, those facts don't prove that he did it alone, but they certainly prove, to my satisfaction, that he was in on it, that he had something to do with it. It's extremely persuasive, and it's persuaded the jury. If I ask you to bet odds, assuming those facts, I think most of you, after reading and reflecting, would be willing to bet pretty good odds that he did it. But if I asked, and if I pressed you the way Bowen used to, with a Bayesian arm-twisting job, I could probably extract from almost all of you a number that you would be willing to bet. I could take various examples and say, would you rather bet this way on a horse race, or on this and this, or this and this happening if you're playing roulette, or bet that Hauptmann was innocent? And I could zero in and make you state a betting quotient, and I'd say, see, that is your confidence. You're confident to the extent of 9 to 1 that he did it. But, I repeat, the fact that I could extract that kind of a subjective betting quotient from you does not mean that you got that number by an algorithm. And in fact, you would all introspect and tell me, no, I didn't get it by an algorithm. And then I would say, well, how the heck did you get it? And you would say, well, you gave me these other goofy examples. And I asked myself, sort of intuitively, impressionistically, gut feeling, is it more likely that so-and-so happened and that Hauptmann did it? And well, I just came up thinking, no, that's less likely, and so that's the way I'll bet. If I had a game of chance to present you so that you're playing blackjack or roulette or caged dice or something, where you know how to compute the probabilities from an algorithm, then of course I can ask, would you rather bet on 37 in roulette or on Hauptmann being innocent? Or suppose I said, I'm going to pay you $8,000 if you're right about Hauptmann, and I'm going to pay you so much in this game of chance. That's another way of doing it. So instead of 2 subjective things, I pair off one subjective one, like the Hauptmann business, with one objective one, where, if you remember your elementary probability theory, you'll be able to think of a number. You'll use an algorithm, and that'll give you a number, and then you will be able to translate that over to the Hauptmann case. But you still have to intuit or gut feeling get an impression about the Hauptmann case before you can make that comparison. So anybody who sits on a jury is doing this, right? You sit on a jury, and there are some facts. If you were on a jury in a wrongful death action, for example, not a murder trial, but a civil action for wrongful death. Now, in that situation, the plaintiff is allowed to bring in insurance tables. And what they do is they say that here you have a 33-year-old man who's in this particular job, and they plot the graph of what has been happening to his salary over the years, and then they extrapolate that and correct for inflation and do all that stuff, and then they say the probability that he would have died if you hadn't run over him with your car when you were drunk is so-and-so for each of these years, and then that's all admitted in our legal system. So that's probability 2, probability of his death, and maybe you can stretch it and say probability that he would get raises based upon the extrapolation of the curve. That gets a little stickier. That's not quite as clear. But from those statistics of what has been happening to his salary and knowing what the life tables say, you would be able to assign the damages. But that doesn't enable you to decide the guilt of the defendant, does it? So the evidence that goes into your action as a member of the jury can include statistics, but the ultimate verdict is a mixture of those statistics and other things about the tire marks and the breath analyzer and all sorts of stuff like that, and what witnesses said and what you told the cop and all that stuff is in this big hopper of data, and it's that the juror has to consider. Now, you mustn't think when I talk that way that I'm only talking about everyday life or about the courts of law, because I include scientific theories as well. That is, we do not have any kind of an algorithm of inductive logic to grind out a number for the probability of Freud's theory of dreams or Piaget's theory of cognitive development in children, or the probability of neo-Darwinism as an account of life, or the probability of the Big Bang being as they now describe it. None of those things is a thing to which the scientist knows how to attach a number. If he does attach a number, he will be doing it in this subjective Bayesian way. That is, he will be doing it as a numerical expression of his gut-level confidence. What odds he would bet. He will not be getting it the way you figure out the games of chance, roulette, or the way you figure out the probability of death from life tables. I had meant to pass out, and I didn't realize I hadn't Xeroxed a batch of them, so I can't do it, but I will do it next time. A nice scientific example. In Snyder's Principles of Heredity, 4th edition, 1950, so it's right before Crick and Watson's thing. And the question is, why do we believe that the genes are located on the chromosomes? Pre-Crick and Watson, and he has a little list of the findings, 8 or 10, 12 facts, a number that when you read through those you think, by God, it must be. Unless there's some spook getting into the act or sunspots, it's got to be the genes have to be strung along in the chromosomes when you look at that set of facts. But if you were required to, and if I said, well, what odds would you bet if you didn't know about Crick and Watson? When you only know the cytology of cell division and reduction division and all that, and the crossing over and the statistics and what you see there, you know, and the cytology, and then you get that isomorphic with what you get from the linkage maps, or you find some things that are supposed to be linked that are linked to each other, but they're not linked to the other stuff that they normally should be in this particular strain of fruit fly, and so you look there, and sure enough, a chunk of the chromosome is chopped off and floating around by itself, and so it's maintaining the linkage, but it isn't linked with these other things it should be, and you think of that, holy smoke, is that ever convincing? And I say, well, what odds would you give that genes are located on chromosomes? The carriers of heredity, genes meaning, let's say, implicitly defined as Mendel's factors. Genes as the carriers of heredity, they're strung along on the chromosomes. What odds would you bet? You'd probably bet 99 to 1, wouldn't you? Well, when you read that Snyder thing, I think you would. And now if I said, well, how did you get that? What algorithm did you use that relates theory to facts, that you could put the facts in and turn on the computer and and it spits out 0.99, and you would say, well, no, I didn't do it that way. Well, how did you do it? Well, you showed me these facts, and I thought, holy smoke, that certainly is convincing. How else could it be? Well, how'd you get this number, 99? Well, I just am willing to bet. That's the best you could do. Well, we'll pass that one out next time. But the same is true of all scientific theories, in that when they are substantive, causal, or historical theories and not merely statements about parameters, which is what a statistical hypothesis is. Remember my diagram. We got T, and then we got H, and then we got the sample, and we got connections between these. And this part is the part for which we have algorithms. That's what you learn about when you take a stat class, and this is the part for which we don't. The relationship between statistical hypothesis corroborated by the facts, and with a certain confidence, if you like. Then we take presupposed H for the moment, and then we're trying to prove T from H, and that part is, in general, not algorithmic. Well, the word that's customarily used in the books for this probability 1 is logical probability. That doesn't mean that the other kind is illogical. It just means it wants to distinguish it from any kind of frequency notion. Logical because it's the logical relationship between evidence and conclusion from evidence. Now, Carnap, in the middle 40s, began to work on concocting an algorithm for doing this. And he worked for many years. He was still polishing it up at the time of his death, about 1970. And I think I mentioned before that most philosophers of science and logicians consider that he really wasted his time, that it's not a doable thing. It's sort of like Einstein trying to do the unified field theory for the last 4 years of his life. On the other hand, if you're a Popperian, you should keep in mind that if a guy as smart as Carnap can't do it, that's very helpful knowledge for us. That gives you a strong reason to think it's not doable. Whereas if some dummy had worked for 20 years, you wouldn't know what you should conclude. So I don't know if there are any people left who think that we could have an algorithm for inductive logic. The way he was doing it was to imagine a perfect language, an ideal language that was capable of expressing unambiguously all of the possible state descriptions, as he called them, of the world. That kind of stems from the early Wittgenstein. You can find the beginnings of that in the Tractatus. And if you imagine this perfect language, which is able to characterize all these state descriptions, then you can use the principle of indifference or the principle of insufficient reason carefully, so as to figure out the probability of various combinations of state descriptions that would constitute a particular subclass of theories. Well, we don't have that language, and we never will. And the idea of figuring out, say, something like the structure of the gene or of the helium nucleus in terms of the kind of notation that Carnap was using strikes most people as kind of hard to imagine. And he, of course, keep in mind, he's not a stupid man. He, of course, realized that you couldn't take any actually going science and play this kind of a game with it. His view was, if we can figure out how to get an algorithm for inductive inference for such a idealized language and such a simple world, then maybe that will give us some insight into how we could do it for the real thing. And that, of course, is not a dumb way to play the game at all. I mean, many advances in science, including in mathematics, are made by saying, let's assume the following, which is far too simple, but we can get a handle on it, and we'll fiddle with it, and then somebody else can come along and do it for the complicated case. So I don't mean to poke fun at R. Carnap for spending all that time. I have a hunch that if he had applied his 180 IQ to something else, it would have been more beneficial for us. But at any rate, I don't run into any philosophers of science who play the who play the Carnap state description game anymore. The late Grover Maxwell, who used to be the director of our Philosophy of Science Center, and who was a sort of passive, quiet, lovable man, but when he made up his mind could be quite firm on occasion. And one time we were in a seminar, and one of the graduate students said, well, that seems to me that you sound like you're really relying on sort of Carnapian state description type argument there. And another graduate student said, well, what's the matter with Carnap's state descriptions? And there was this silence, and Maxwell said, what's the matter with Carnap's state descriptions? They're horseshit. That's what's the matter with Carnap's state descriptions. And that was the end of that. That was the end of that conversation. Lovely. Takes a certain courage to deal with it that way. Now, if we say that it appears on the surface, at least, that probability and probability 2 and probability 1 are quite different kinds of animal, and secondly, that we can't dispense with either of them either. We need probability 1 for evaluating scientific theories and legal matters and in our own daily life. I gave examples of that. Should I propose to Henrietta? Should I take graduate work at Yale? Should I quit psychology and become a geneticist, et cetera, et cetera? Should I buy a Swedish car? We have to have both, and as Bishop Butler says, the only time I ever saw Carnap quote a bishop, probability is the guide of life, says Bishop Butler, which it certainly is. And I mean, if you couldn't make daily decisions like even fasten your seatbelt or come over here on a bad day or whatever without the concept of probability in the background, you'd be immobilized. I mean, if we all had to act on certainty, you couldn't do anything. I mean, you couldn't safely stay in a adult Skinner box because you wouldn't know what the probability was that you developed schizophrenia or something. So probability is the guide of life, and we have to have both kinds. Question. Although on the face of it they look so very different, and it seems like it seems impossible to imagine computing this by some algorithm as the way you do in a roulette game, how come they have the same name attached? That's a little strange, isn't it? I mean, von Mises says people use the word probability carelessly to refer to things that are not limits of relative frequency, and if they read my book, they'd quit talking that way. Shame on you for talking about probability when you don't have an infinitely extensible series which has a certain limit and which follows the principle of randomness. Oh, by the way, that principle of randomness, or the fact that no place selection will give you a different value for the limit, has another famous name that I didn't mention. It's called the principle of the impossibility of a gambling system. And it's actually called that way in the statistics books, frequently with caps. The reason that the king of Monaco doesn't have to worry about going broke is the principle of the impossibility of a gambling system. And in the long run, if you play the rest of your natural life at Las Vegas, you will be in the red almost certainly. Not with p = 1, of course. You could be one of the lucky people. How come we have the same word? Now, Reichenbach, a frequentist like von Mises, and accepting the same definition, the limit of a relative frequency as this series is indefinitely extended, the limit of f over n as n increases indefinitely is p, probability pi. And that definition is both Reichenbach's and von Mises. But Reichenbach was much more gutsy than von Mises in a different way. Instead of saying people who use the word probability to mean probability 1 should quit, he said, no, that's all right, they can do that, because I'm going to try to show that probability 1 is really probability 2. And if you want to see his heroic efforts to do that, see his book on probability, 1946, or his experience and prediction, the one I keep mentioning, 1938. I won't go through his efforts, which are very clever and quite persuasive unless you go back and read Carnap to counteract them. He tries to show that in the case, for instance, of scientific theories, that if you were to characterize scientific theories by their possession of certain attributes, and it's very vague about the attributes, I take it means both their intrinsic attributes as well as their relation to facts attributes. It must include the second. But it must also include some of the first, because there are certain kinds of theories that you would consider highly improbable because of their intrinsic content. If I propose to you that instead of Lactobacillus bulgaricus curdling the milk, it was brownies, you would not countenance that as having enough prior that you'd even look into it, whereas in the 12th century you might have. He says, his notion was that if we had a souped-up method of characterizing scientific theories that would enable us to say that a certain theory has attributes A1, A2, A3, blah, 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 and it lacks A7, A9, A11, and the like, that it would turn out that scientific theories that have certain combinations of attributes, present and absent, would have a higher truth frequency than those that have other combinations of attributes. That was the idea. He never tried to deliver on that by making any empirical studies. That's partly because, you see, being a logical empiricist, he thought you could do it from the armchair and you wouldn't have to study the history of science, which is a little funny if your position is that you hold that you can reduce probability 1 to probability 2 on the basis of the actual success frequency of theories. I mean, then you've got to get out of your armchair and go to the history of science books. On the other hand, one can't fault him too much for not delivering the goods on just how you do this, because you could say that's not any wackier than Carnap's damn state descriptions, though neither one of them is capable of being used to assess any actual real-life, flesh-and-blood scientific theory. I can't do that any better with Carnap's phony algorithms, with his state descriptions, than I can do it with Reichenbach's idea that theories have certain properties. And if they have those properties, they're going to turn out, whereas if they don't, they're going to be falsified. This is called the identity conception. I don't know how many Reichenbachians there are in the world. They are certainly a minority. They are probably not as small a minority as people who believe in Carnap's state descriptions, but one knows from talking with philosophers and logicians that there aren't very many people who hold to the identity conception. If this is getting a little confusing, that's not today because I'm explaining it badly. Today it's because it's the nature of the darn problem. It's most embarrassing that some of the most fundamental concepts we have in human thought are fuzzy. You normally think that the derivative ones would be fuzzy, but it's the rock-bottom ones that are frequently fuzzy, and many philosophers have commented upon that fact. I mean, one of the most basic concepts we have is the notion of causality, which Kant, of course, thought you had that a priori. Do we have a clear conception of what we mean about the difference between causality and, quote, mere correlation? There is certainly a distinction. If there weren't, you wouldn't bother doing an analysis of covariance, would you? Or a partial correlation, or matching, and so on. So there is a difference between mere correlation and causality. But to say precisely what that is, exactly what it is to say that there's a causal arrow between event E1 and E2, the boys and girls are still struggling with it, and nobody knows exactly how to do it yet. So don't be sad about that. The fact that this is a basic concept for us, especially in social science, don't be sad about the fact that it's still kind of muddy, because the rock bottom things are usually kind of muddy. Well, I am told, I'm not much of a linguist, but I am told that this is not merely true of English, it's true of French and Polish and Russian, and I don't know about the Oriental languages, that while there are some other distinctions made, there is a use of probability that refers both to probability 1 and probability 2. In German, for example, Wahrscheinlichkeit is used in both ways. So that's a little spooky. You think, if these two things, if we assume Reichenbach is wrong, and the identity conception won't wash, this is a metalinguistic concept regarding the connection between propositions, and this is an object-linguistic concept regarding frequencies of events, and never the twain shall meet. How come we got the same word? And last time I hassled Carnap before his death, I pressed that on him and said, why on earth is it the same? And he said, Paul Meehl, fair betting odds. So in that sense, he sounded like a Bayesian subjectivist, which Carnap certainly was not. Fair betting odds. Meaning that if you insist that there must be something in common between these, in spite of the fact that this is algorithmic, frequency-based object linguistic, refers to happenings, this is metalinguistic, not algorithmic, not a relative frequency, that they must be linked in some way, otherwise it would be a puzzler why the same word is used. I don't mean that's a hard proof, but it certainly makes you suspicious. The common core, says Carnap, is that they both lead to the definition of a fair bet. That doesn't mean that we define either one of them in terms of a fair bet. The subjective Bayesians do it that way. Carnap would not, but they both lead to saying what is a fair bet. If you are highly confident in a certain theory, then you will bet 9 to 1 or 95 to 5, just as if you have a relative frequency of something happening that's 95 to 5, you'll be willing to lay wagers on that basis. I don't want to get into the problem about the marginal utility of money and so on, which complicates things further. God forbid we should get into that. So, I asked Carnap, does that mean that if omniscient Jones knows the truth and falsity of theories, that if an algorithm for probability 1 were to be worked out, not by Carnap, but by O.J., a really rich one that would do it, for expressing how evidence supports theories, would the classes of theories that have different p-values, numerifying probability 1 now, not gut feeling, but by God's algorithm, how well does evidence really support a theory, if you know how to do inductive logic. If we classified theories as to their omniscient Jones inductive logic support, probability 1, would they be ordered in the same way as groups of theories as relative frequencies? Would the theories that have 9 to 1, P1, probability 1, algorithmic result, tend to be true in the eyes of God 90% of the time, and those that have 6 to 4 be true in the eyes of omniscient Jones 60% of the time? And Carnap said, yes, it should.
With omniscient Jones, it seems to me like both of these probabilities, whatever numbers or decimal numbers we would put on them here, omniscient Jones, all the probabilities would reduce to either 0 or 1.
Oh, yes. I'm not saying that omniscient Jones would have any trouble laying bets. He knows what's going to happen. Yes. Well, yeah, there is that funny exception about that one. I don't know why you had to put that question. There is a funny exception about that one. If omniscient Jones is defined atemporally, as say Aquinas would say, God is outside of time and so on, sees everything at once, then you would be right. If omniscient Jones is not considered to be outside of time, but to know all particulars up to this point in time, then that would depend upon whether quantum uncertain events are truly indeterminate or not. But if you leave out the quantum case, the answer, of course, is yes. If somebody knows all the particulars, obviously none of these things are merely probable. However, what I meant is that omniscient Jones, looking at the dice, knows what the relative frequency is, right? Even though he can also predict the individual throw. So that let me stay with this for the moment. Omniscient Jones knows what's going to come up. Well, take the nice case where I'm not omniscient, but I'm a crooked croupier at Vegas, and I know exactly which number is going to come up each time. I also can state a relative frequency, right? And I will. In fact, I'll have to see to it that the relative frequencies come up. Otherwise, people are going to catch the fact that the wheel is biased, so that I can be in cahoots with somebody who's out there betting, and he will win every time. And I know what's going to. I know that's going to be 37 the next time and 00 the next time after that. But that doesn't falsify a probability statement here, does it? Now here, what omniscient Jones knows is what is the semantical and syntactical, well, semantical includes syntactical. What he would know that even though he doesn't have to rely on it. He would know how well the evidence supports this, just as, well, I think of the Clinical Pathological Conference in medicine. Those of you who are clinicians, if you have never read any of those, you ought to. You ought to really, in fact, you ought to go to some of those outside of psychiatry and go to a good one for a change. And like in the neurology or internal medicine. And now there, the physicians are sitting around and they're talking about the presenting complaints and what the lab tests showed and so forth. And people are asked their opinions. The famous one at Mass General Hospital is published every week in the New England Journal of Medicine. And if they have a visiting fireman from Berlin, they put him on the spot. What do you think, Dr. Schiefelbein? And he thinks, I think this is milk syndrome, but it could be Fisby's disease, and blah, 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 blah. And then comes in the pathologist with the guy's brain and liver on the plate, you know. And then he puts up the slides, and we find out who's right. And it's a very good education for physicians. We can't, unfortunately, you see in psychiatry, you say, see those holes in the superego up there on the right-hand side? All right, now you see the pathologist knows the answer. He knows that the guy had Fisby's disease rather than Hockheimer's. But even though he knows the answer, he also may have very definite ideas as to the relationship between the clinical data and the answer, right? He doesn't have to use the algorithm, but he knows whether they're departing from it. They used to pull a cute one at Mass General for many years. The chief of pathology there was a man named Castleman. 3 or 4 books written by him that are from the Mass General case conferences. And every once in a while they would put Castleman on the pan. He would not be allowed to talk to the other pathologists, and he'd have to play doctor. And he was very good indeed. It was interesting. He was very good indeed, although he had not examined anybody he hadn't touched anybody but dead patients for 50 years. But he was very good as a clinical diagnostician. So omniscient Jones knows the single events, and he also knows which scientific theories are true, but that doesn't prevent him from knowing what the relative frequency of the dice is, nor does it prevent him from knowing whether people are departing from the ideal algorithm, which, if they, in their lack of omniscience, would practice, would maximize their odds. Now, to steer clear of omniscient Jones for the moment, take a real-life possibility, which one could actually do if you thought it was worthwhile. It would be kind of fun. Suppose you take a huge collection of murder trials in which subsequent evidence has made it clear with probability 0.99 who really did it. That is, for example, let's say either the person tried or somebody else confesses, which isn't perfect proof. Crazy people can confess at times. But by and large, people don't confess to murder unless they did it. But some crazy people have done so. But let's say we have the further evidence that can sometimes pop up. The guy said, yes, Smith is in the pen for this, but I'm the one that did it. George and I did it, and we did it to get the bonds. And the bonds are in a tin box, which are 15 feet from the oak tree, a la Edgar Allan Poe and the Gold Bug, you know, and you go, FBI goes out and digs up the box, and there are the bonds, and this guy's fingerprints are on it. And I can pile it up so it's clear that this person who confessed is the murderer. I mean, he knows facts nobody else would know, and his prints are on the box. And so if we imagine a series of 1,000 murder trials in which people were convicted in 500 of them and acquitted in the other 500, and in which either the person himself or some other person confesses and presents evidence of this highly convincing kind. So we say we're as certain as you ever are in human affairs who really did it. Now suppose that we had some kind of a crude algorithm for inductive logic that we were using, that the jury was using during the trial. We had some souped-up Carnap thing. Actually, a French mathematician, Poisson, after whom the Poisson series is named, wrote a treatise on the probability of evidence in courts of law. And he was trying to use the probability calculus to actually assign p-values to a certain person being guilty, or whether 3 witnesses was how much better than 1 witness and stuff like that. I've never read the book, but in fact I don't think it's ever been Englished. It was a classic effort. People now look upon it as being kind of silly that he thought you could do that. Like Laplace, another mad genius, used the rule of succession to compute the probability that the sun would rise tomorrow, which is a goofy thing to do. But if you apply Bayes' theorem, and in certain ways, you can get that the probability is m plus 1 over m plus 2. Is that the way it goes? And so if you start the sun having risen according to Bishop Ussher's date for Genesis is 4004 BC at 9 o'clock in the morning, you can figure out that there's a high probability that the sun will rise tomorrow. Well, everybody today says that's an absurd use of the calculus of probability. I mean, that just doesn't wash. Well, we can conceive, aside from Omniscient and Jones, we can conceive of this 1,000 trials as being now arranged in terms of the algorithm that the jury used, souped-up Carnap inductive logic machine. And then we can ask, what's the percentage of correct judgments made, right? We take all of those for which the algorithm gave us a probability of between 9 and 9.9, between 8 and 8.9, between 7 and 7.9 of whatever the verdict was, guilty or innocent. And we can look to see what the proportion of times was that the jury came to the right result. Suppose that that correlation were 0 or negligible. What would we do? Well, if we had 1,000, if you don't like that, take 5,000. If the correlation between the inductive logic algorithm and the frequency of being right, frequency, probability too, was negligible or 0, you would conclude that your algorithm was no good, right? And in that sense, in that strange but powerful sense, you can see why Reichenbach and company think that the frequency notion is still the basic idea behind it all. Because if I said that the algorithmic computation, saying nothing about frequencies but how evidence supports conclusions, if the application of that procedure led to not being right any more often than being wrong, so that the relative frequency of being wrong was just as high when the algorithm gave me 0.9 as when it gave me 0.51 to 49, we would conclude the algorithm was no damn good, right? We would say, this is not actually giving us the probability of something upon the evidence, because if it were, then when we had really high values, we should tend to be right more often, which we're not. So there is that core, basic metaphysical sense in which the idea of relative frequency is there. And as I say, Carnap didn't drag his feet at all. When I pushed him on that, he said, well, yeah, that's fair betting odds. Betting odds cannot be fair if the frequency in the long run is such that you'll be in the red. That's why the Finetti and the subjectivists, their criterion of rationality, since they say that you can, they seem to be saying that you can pick the initial ones any damn way you want. I can't believe they really mean that. But their criterion of rationality is coherence, and coherence for those guys means that you must not be stating odds on various events such that another gambler could make what they call a Dutch book against you. That is, he could arrange he could offer you various bets such that you would be certain to lose. That's called a Dutch book. And so we would, if there was a method of evaluating the support given to hypotheses by data that was algorithmic, that yielded a probability number, so that you were advised, don't go by your gut level intuitions the way Professor Bowen extracts them from you. Use this souped up super Carnap way. You put the facts in there and the computer spits out P equals 73. That tells you your rational betting odds. If it turned out over a long series of such judgments, applying such an algorithm of inductive inference, that it was unrelated to the relative frequency of being correct, then we would say that algorithm is no good for computing probability 1, because in the long run, probability 1, if the values are right, ought to tend to be right in the sense of relative frequency. So that when the followers of Reichenbach insisted that the core idea was the limit of a relative frequency, held the identity conception, it isn't quite as goofy as it sounds, since when pressed, somebody like Carnap, insisting on the distinction, nevertheless admits that although they're conceptually distinct, this one has to be correlated with this one. And in the long run, very highly. Presumably, in billions of, if there were billions of scientific theories around, it should be correlated, if you had a good algorithm, it should be correlated practically perfectly, shouldn't it? I mean, what would make it not be correlated practically perfectly if you had the right algorithm? All right. So much for that. Interesting problem. A nice summary. Well, now I can't remember the fellow's name, so I'll tell you next time. Does anybody know the book called, by Vic, somebody, a Britisher, called Comparative Statistical Inference? Anybody know? Vic Barnett. Vic Barnett, Comparative Statistical Inference, 1973 or thereabouts. It's got a beautiful, brief treatment of this business. It's also got a gorgeous treatment of the difference between Fisherians and Neyman-Kolstad, Neyman-Pearsonites and the like. Excellent, very well written, and fair-minded man. All right. Now, if there was anything else I wanted to say about probability, I don't know what it is. No, I have an uncomfortable feeling there was another major point I wanted to make, but I can't do it. Now that provides a good background for the remaining topic for this quarter, which is on one of my favorite subjects, on the subject of clinical and statistical prediction. I became interested in, this is a little autobiographical remark for starters. I became interested in this topic already as a graduate student because I was, as I think I've told you before, I got interested in psychology in my teens via reading Carl Menninger, The Human Mind, and then reading a lot of Freud. And then I hit this behaviorist psychometric anti-Freudian department, which was even more so when I was a student. So what was I going to do? I mean, that presents real strong cognitive dissonance if you're halfway bright. I got into this field because I was interested in the mind, and there isn't one. And, and as the joke used to be, speaking of Watson's theory that thought was subvocal speech, that John B. Watson has made up his windpipe, that there is no mind. And so there I was, and so I had to, and then I got, when I became, worked for Dr. Hathaway over at the hospital, he was so anti-Freudian he could hardly spell Freud's name, and so here, that's what got me into this business, and nobody liked it. And so I had to get my act together, and when I started teaching the introductory course in clinical psychology in 1944, before my PhD, because Howard Hunt got drafted, and I was 4F, God be praised, for a heart lesion. The very first time I taught that course, I spent 2 or 3 sessions on the problem of clinical and statistical prediction. And I thought about it and read about it for 10 years or so, and in 1954 I published this little book, which is out of print, Clinical versus Statistical Prediction. And by the University of Minnesota Press, which accepted it because I was by then chairman of the department, and they did me a favor. I had no success in getting a publisher because people said it wouldn't sell, and I believe I told you that the last printing before it went out of print, it had, well, this one doesn't say. It had, I think, gone through 7 printings and sold 13,000 copies. And so it was a fun thing to think about, and still is for me, although the studies are getting boring because they all come out the same. And I also have reason to like the subject because it made me a fairly famous psychologist at an early age, infamous in some quarters. I was told by one of my colleagues that practically the whole clinical faculty at Michigan went into a reactive depression after reading Meehl's book. People perceived me as writing this to beat up on the clinician, which shows how distorted the mind can get, because if you do a page count, you will find there is more effort and time spent in that book explaining what the clinician does that the clerk or the computer, well, I wasn't talking about computers in 1954, can't do than the other way around. It's actually, in terms of total time spent, more a defense of the clinician than it is an attack. But the chapter that summarized the empirical data, which were not mine, I couldn't help it how the studies came out, made the clinician look pretty punk. And so the idea was Meehl is one of those damn Minnesota statistician types that doesn't believe in the soul, and all of which is quite wrong. Okay, that's about me. Now, I am under contract and have been for several years to update it, and I am in the process. And my colleague, former student Will Grove, is currently doing a big meta-analysis and is now up to 127 studies and estimates by extrapolation, I think he's up to the letter S, that he will have in the neighborhood of 150 studies. And so that will motivate me to get my act together and finish writing a new edition, which will, because of its sort of classic character, the U Press has told me, why don't you just leave it as it is, don't revise it, and stick some more chapters on the end. So that's what we're going to do. So I'll be answering my critics as well as presenting the studies, which at the time the book was published were only 18 or 20 in number. And now there are 150 of them. Well, let me formulate the question for starters. you are trying to predict somebody's behavior. For instance, you are on a committee of the law school, and you're selecting applicants to go to law school, and you have their law school aptitude test, you have their grades from a certain undergraduate college, and you've got some letters of recommendation. And the question is, who gets in? Or you are a psychologist or social worker on a parole board, and you have this criminal offender who has committed a couple of armed robberies and is a dangerous customer and has been in the clink so many years and has been a pretty good model prisoner, hasn't assaulted anybody, hasn't broken any of the rules, participates in group therapy where he learns to say, I've got in touch with my feelings. I've learned my lesson. And so the question is whether to let him out before his full time is up. It's obvious that to make a mistake about that is very serious. It costs a lot of money to keep a person in Stillwater, and it's not pleasant for him or for his friends and relatives. On the other hand, if you let him out and he robs another bank and maybe this time around kills the cashier, that's a pretty serious mistake too. Or the problem is whether to hospitalize a depressed patient. The lifetime risk for people with a major affective disorder for suicide is 1 in 6, which is Russian roulette probabilities. Yet we don't like to put people in a hospital for a variety of reasons, both psychological, social, and economic, if we can avoid it. So the question is, should this patient be seen on an outpatient basis, or don't we dare to leave him out? Is he going to do himself in? Or we have a depressed patient who has not responded to, say, Elavil or a couple others, and we're running out of meds, and we know from the statistics that there's a subset of depressed people who are non-responders to the antidepressant drugs, but who respond well to electroconvulsive shock. Do we blitz them, as we used to say? That's a major kind of intervention. Nobody, even people who've done it for years, really kind of, psychiatrists even don't quite like the idea of making somebody have a fit, grand mal fit, even though they soften it now with an Nectin, so the patient doesn't break his bones. But running 200 milliamps through somebody's brain to make him have a grand mal seizure is something that goes against the grain. I have never regretted not going to medical school. I've had a lot more fun being a clinical psychologist, but one of the best things about not having an MD is that you never have to push that damn button and make somebody have a fit, because the evidence is quite clear that there are some depressive patients for whom that's the treatment of choice, whether we like it or not. So here you have some serious decisions about people's careers. Somebody wants to go to graduate school, you tell them no. Wants to go to dental school, you don't let them in. You parole a criminal, maybe he'll rape somebody. A patient kills himself because you leave him on an outpatient treatment basis, and the like. So we are constantly in the process of deciding about how a human being will react under certain circumstances. Now, one of the things that a couple of critics said when my book first appeared was that we don't just predict or forecast in clinical work, because our aim as practitioners is to help rather than just guess the future. That means we want to change the probabilities, which means that we want to, if possible, falsify our initial predictions. That sounds like a clever remark, but it's a stupid one, because, of course, every time I apply any measure of intervention, what am I doing? I am predicting that something will happen if I do it that's different from what will happen if I refrain from doing it. In fact, not doing anything following the old medieval principle of medicine, primum non nocere, first of all, don't do any harm, which is sometimes the best prescription. I remember the chief psychiatrist in the Student Health Service once telling me that he had a sign on his desk. The patient couldn't see it, but he had said, "We don't monkey with anybody's mind unless there's really something wrong with it, and even then we should be damn careful," it said. And so the point is that not to intervene is a form of behaving. I mean, there's a finite set of things that the clinician or the counselor or the surgeon or the economist or your CPA or your lawyer can do. One of them is not to do anything. And the choosing of which thing to do, including sitting still, not doing anything, is presumably based on some belief, rational or not, as to what will happen for each one of these options. So the argument that we don't merely predict, we want to control or change, is a fallacious argument. Of course we want to control or change, but rational efforts to control or change always involve an element of prediction. It may be implicit. Usually it's quite explicit, isn't it? We'll give them Elavil instead of Valium because we think there's more depression here than there is anxiety or whatever. So all choices that we make in the clinic or in the parole board or in a graduate student selection committee are, if they're rational, predicated upon some kind of predictive belief that we have, that if we do so-and-so, then such and such will happen. Whereas if we do something else, then this such and such won't happen, or at least is not as likely to happen as if we did the first thing. Now, all such predictions are probabilistic in character and are likely to remain so. Sometimes you hear people say that psychology is such a young science. It ain't that young anymore, by the way, but anyway, been around for quite a while now, and it should be doing better than we are. But the notion is that someday it will be able to predict in the same sense that classical mechanics is able to predict. And I don't run into very many people that have that delusion anymore, so I'm going to assume that nobody here has it either. Although, of course, there are certain kinds of situations with sufficient stimulus control and with a sufficiently simple organism that you can predict with extremely high accuracy, thus the shape of a cumulative record in a Skinner box. But predicting the behavior of the people in this room, socially, financially, sexually, and otherwise, is never going to be a for sure proposition. And there are many physical sciences in which it's assumed that it's always going to be probabilistic, such as meteorology. There are no meteorologists who say, if we only learn enough about clouds, we will be able to predict like Hooke's law. You don't find anybody saying that. The argument is to whether how much theory you should use in your statistical predictions. That, apparently, there's still a controversy about. But there's no weather predictor that says if we were only smarter, we would do 0.99. As you probably know, weather prediction is only about 15% better than so-called persistence prediction. Persistence prediction being defined as going to be tomorrow pretty much like today. And in most weather stations, they run about a 15% better, 10 to 15% better batting average. Minneapolis, the Twin Cities, has a rather bad place for weather prediction. I don't know the theory behind that. Some other places are a lot easier. So these predictions about human conduct, criminal behavior, educational success, response to medical treatments, are always going to be of a probabilistic or statistical nature. And that takes care of one form of objection to my views. When somebody says, I don't want to predict statistically, I want to know for sure about this individual, and the answer is, you ain't going to do that, buddy. And so what you're telling me is that you want to know with better probability than I can give you about this individual. That's a meaningful remark. But to say, I'm not interested in probabilities but only certainties, then you've got to get out of the psychology business and make your living in some other honest way, because it's going to be impossible for you to state p-values of 0.998. Well, how do we do it? we got some data, and we have a defined predictive task. I'll come later to the case when the predictive task is open-ended. That's one of the best ones for the clinician. We'll deal with that later. But usually we have, and we do in the situations I mentioned, a closed outcome set. Patient responds or doesn't to shock treatment. Criminal recidivates or doesn't. If you want to talk about the seriousness, you can break that up into subdivisions. Criminal commits one of the 7 major crimes of the Unified Crime Index, or he commits a gross misdemeanor instead, not as serious. So you can break those up. But you have finite set of outcomes before you, and you're going to act on the basis of a p-value connected with this person having each of those outcomes. The way most such judgments are arrived at is informal, or what in the book I called clinical, not implying bedside, which is the literal meaning. If you don't like the medical connotations of the word clinical, all right, just call it informal. In an informal prediction method, say we've got this student applying for law school, and the committee is the assistant dean and 2 of the profs, and they're sitting there. I assume it looks the same way it does when we pick people to go into clinical psych in this department. And they're sitting there, and here's a score on the law school aptitude test, and it just happens he has a GRE as well. Files don't always have that, and here are his grades at West Overshoe College, and you got a I don't like that C in poli-sci there for a lawyer. What do you suppose was the matter there? But most of the A's, yeah, pretty good. And here's a letter from Professor Glotz. Says, this guy is terribly bright, but I can't stand the sight of him. What are you going to do about that? And so on. And then there's a discussion. In the old days in a smoke-filled room. Now it isn't smoke-filled. And some sort of a decision is made by a show of hands or in a case conference by the chief sawbones, and action is taken accordingly. That is the informal or impressionistic way of combining data to arrive at a predictive judgment. And on a given day in the United States, of all the judgments that are made about human conduct, you can safely assume that the proportion that are made that way must be at least 99.9%, right? At least. Lower bound. 999 out of 1,000 are made that way. Whether it's by an individual or by a group, individual just turns the data over in his mind and reflects. The group argues with each other. So that informal way of data combination is the, you might say, usual, standard, accepted mode of arriving at a prediction about human behavior. It's the normal way. It's the way that seems most natural to people. To most people unfamiliar with this controversy, it's the only way. Many people, it doesn't occur that there's any other way you could go about this. Now, I said, given a set of data, and I want to emphasize the distinction between the kind of data and the mode of combining them. The kind of data can be anything you want. It can be interviews. It can be life history data. How many times has a person been arrested? Did he graduate with honors? It can be some formalized rating system by interviewers, or it can be in a narrative form. It can be a checklist. It can be mental tests, the MMPI, the graduate record. Whether it's whether the data that you get as a decision maker are psychometric or life history or some kind of behavior sample, a work product, social impact data. That's what a letter of recommendation amounts to. That's not what the person did. It's whatever he did hit somebody in a certain way. I assume that you all know what the industrial psychologists have shown about that beginning back in 1925, and that is that except for extreme values of the letters or people that you've calibrated, you should throw them in the wastebasket. Despite that, the department continues to get these letters and sit around and look at them, and the research is massive and consistent that you should burn them. Unless you've calibrated the writer. If I got a letter from Gardner Lindsay that I know very well and was here for several years, and I know he had very high standards and a very honest guy, and he says this is the smartest PhD we've had around here for a long time, I will tend to believe that. Most people, I don't pay any attention to it. You should see the letters we get on people looking for a job in this department. It's practically every one is Freud, Thurstone, and Skinner rolled into one. It's bizarre. It's just bizarre. And the faculty persists in reading this damn nonsense. You know, I don't read them anymore. And the evidence shows that they have no validity. But at the extremes, especially the bad extremes, because of the people do not tend to say this is a dope or a jerk, you see. And if you've got to be careful of that, because it might have been a particular professor that is an authoritarian intellectually, and the guy rubs in the wrong way, and so he thinks he doesn't agree with my theories, he must be dumb. And so you got to be careful. But if 3 or 4 different people say, you know, this guy, I don't know how he got through, got a BA, I mean, he is so stupid, then I take that quite seriously. Or if I have calibrated the writer, I take it seriously. Other than that, you should throw him in the wastebasket. That's what the evidence shows. People continue to rely on them. People continue to, they do it. It takes time, even though they have no validity. Now, the other method, well, so let's be very clear about this. We are not talking about psychometrics. Some of the people that reviewed the book and people who write articles about it today still get that wrong, and that means that they didn't read it with any care. We got psychometrics and non-psychometric data, and then you can combine it in this informal way, or you can combine it in some formal mechanical way. And the usual combination is a combination of psychometric and non-psychometric combined informally. That's the usual way of doing it. But you have to distinguish between the kind of data and the mode of combining the data. And what the controversy is about in this area is not this, but this. How do you put the data together, whatever the data may be? They may not be mental tests. Usually, if we're psychologists, they will be both mental tests and other kinds of data. It's taken me 20 years to get Anna Anastasi to write her damn book in such a way that she doesn't say Meehl thinks you should always predict from mental tests. I think the last edition she finally got clear about that that's not what I am talking about. So it could be, for instance, that you have very little faith in psychometrics for predicting a certain domain and would rather rely on documents from the life history, like a school record or ratings by the peer group. That doesn't tell us how you should combine that information for predictive purposes. So what I will start with next time, I wish I had got to that stuff on the board, but I haven't, and I can't. Next time I'll start with the other way of doing it, which is a mechanical way, in which once the data are somehow encoded, and that doesn't have to be anything fancy, you know, it doesn't have to be scaling, it can simply be if there's a mention of a criminal conviction, code 1, if not 0. Once the data are encoded, then we have an algorithm for putting those coded data together to assign a p-value to an outcome. And that's the mechanical mode, which is usually referred to as the actuarial or statistical mode of prediction, but isn't quite always actuarial, because I can write a mechanical procedure from the armchair. I can sit down and say I'm going to give these three things twice as much weight as these three things, but when you encode your data, you will be multiplying these three by 2 and these by 1 and adding them up. And if somebody says, where did you get those weights? I might tell you, well, I made them up out of my head from my clinical experience. That is an algorithm and hence an actuarial method, but the way of deriving that algorithm is from clinical experience. So what we're talking about when we speak of the actuarial method, actuarial or statistical, is a little loose, because the generic class here is a mechanical or algorithmic method, leaving open how you got the weights and whether it's linear or nonlinear and so forth. And then we'll talk about that next time. Okay.